Good day, everyone. I am Micaela Laresa, and I will be discuss the energy consideration in rotational motion. My learning objective is A. Understand the concept of work and energy in rotational motion. B. Apply the work kinetic energy theorem to rotational motion. C. Analyze the relationship between Turkey, angular displacement, and work done. And D. Apply energy principle to rotational situation. And E. Calculate angular speed and tangential speed in rotational motion. So let's have a recap or short recap for the keywords. Translational motion. Translational motion involves the movement of an object from one point to another in a straight line. It is characterized by displacement, velocity, and acceleration. Next is work in translational motion. Work is done on an object when a force is applied and the object moves in the direction of the force. The work done, or W, is calculated as the product of the force F and displacement D in direction of the force. W equal F dot D. Or should I say work work done equal force dot displacement. So next is the kinetic energy. Kinetic energy is the energy possessed by an object due to its motion. For an object with mass m and velocity is v, kinetic energy is given by kinetic energy equal 1 half or mv, or should I say mass and velocity squared. Next is next is potential energy. Potential energy is the energy an object possesses due to its position or condition. Gravitational potential energy is often discussed in the context of translational motion, and it's given by Pe potential energy equal mgh, where m is the mass, g is acceleration due to the gravity, and h is a height. Next, last but not the least, the conservation of energy. The principle of conservation of energy states that the total energy of a closed system remains constant over time. In translational motion, this means the sum of kinetic and potential energy is a constant if no external forces, like friction or air resistance, are active. Next, everyday objects and systems involve rotational motion, such as a wheel, gear, and rotation of planets. Understanding energy principles in rotational motion is essential for designing and analyzing these systems. Next, in translational motion, we found energy and concept, and in particular the reduction of the conservation of energy, equation called the work kinetic energy theorem, to be extremely useful in describing the motion of a system. Energy concept can be equally useful in simplifying the analysis of rotational motion. From the conservation of energy equation, we accept that for a rotation of an object about a fixed axis, the work done by external force on the object will equal the change in the rotational kinetic energy, as long as energy is not stored by any other means. To show that this case is the fact true, we we begin by finding an expression for the work done by a turkey. So this example considered a repeat object pivoted at the point of zero or 0 in the figure 10.19, suppose a single external force, F. Makikita mo yung F doon na nakaturo sa arrow. It is applied at the point of P and D and S. This is the displacement of the point of application of the force. And the small amount of work or dW done on the object by F as the point of application rotation through an infinitesimal distance. Or ds equals rd 0 in a time interval or dt is. In addition to the work kinetic energy theorem, other energy principles can also be applied to the rotational situation. For example, if a system involving rotational object is isolated and non-conservative force act within the system. The system. The isolated systems model and the principle of conservation of mechanical energy can be used to analyze the systems, as in the example. We finished this discussion of energy concept for rotation to investigating the rate at which work is being done by F on the object rotating about the fixed axis. This rate is obtained by dividing the left and right side. And this is the dw over dt equals r d data over dt. The equation of dw dash dt is by definition the instantaneous power P delivered by the force. Furthermore, because d data over dt equal dw. So next, this is the example of the rotation rod. So, so this is the example of rotating rod. A uniform rod of length L and the mass M is free to rotate on the friction pin passing through one end. The rod is released from the rest in the horizontal position. What is the angular speed when the rod reaches the lower position? So, so this is the solution. Conceptualize considering the figure, or should I say that the picture. The image, the rod rotating downward to a quarter turn about the pivot at the left end. The angular acceleration of the rod is not a constant. Therefore, the kinematic equation for rotation cannot be used to solve this example. We categorize the systems of the rod and the Earth is an isolated system in terms of energy, with no non-conservation force acting and use the principle of conservation of mechanical energy. We use the configuration in which in the road hanging straight down as the reference configuration for the gravity, potential energy, and assign a value of 0 for this configuration where the road is the horizontal position. It is a non-rotational kinetic energy. The potential energy of the systems in the configuration relative to the reference configuration is mgl dash 2 because the center of the mass road is the height of length dash 2 higher than its position in the reference configuration of inertia of the road about an axis passing through the pivot. Use the isolated systems or energy model. Write a conserved biomechanical energy equation for the system. Ito yung K1, Ki plus 2I equal Ki plus Ui. Substituent for each the energized and solve for an W and use I equal 1 third ml squared. For the road, see the table 10.2. Magiging 1 half IW2 plus 0 equals 0 plus 1 half MGL. Magiging parang ang magiging solution niya ay W equal MGL over I square root, then equal MGL over 1 third ML squared square root equal 3G over L square root. So B, let's about letter B. Determine the tangential speed of the center of mass and tangential speed of the lowest point on the road when it is the vertical position. Use the equation and the result from part A. Because R for the lowest point on the road is twice. What is for the center of mass? The lowest point was the tangential speed. Twice that the center of mass, like UCM equals IW equal 1 L over 2 W equal 1 half square root 3 GL. Then U equal 2 UCM equal 3 GL square root. Finalize, applying an energy approach allow us to find angular speed of the road at the lowest point. Convince yourself that you would find an angular speed on the road at the angular position by knowing the location of the center of mass at this position. So next is the work. I will discuss the new concept or the should I say each step by step. So work done by torque. Work done by torque in rotational motion. Work done by torque is a similar to the concept of work done in translational motion. The work done or dW by a torque during an infinitial rotation is given by the formula dW equal TD data, where d data is the angular displacement. Torque is the rotational equivalent of force, and it represents the tendency of a force to rotate an object around an axis. Relationship between torque, angular displacement, and rotational kinetic energy. The rotational kinetic energy or Ke of an object is related to torque and angular displacement. The work kinetic energy theorem for the rational motion states the work done by torque is equal to change in rotational kinetic energy. And this is the formula. W equal Ke. Mathematically, this is expressed as torque uh, d data equal 1 half I the W 2 over I, then double minus W2 over I, where I is the moment of inertia and W is the angular velocity. Next, application of the work kinetic energy theorem in rotational motion. The work kinetic energy theorem for rotational motion is applied to situations where torque is involved. It allows us to relate the work done by external force torque to the change in rotational kinetic energy of an object. Next is the conversions of mechanical energy in rotational system. If an isolated systems involving rotating objects experience no non-conservative force, the principle of conservation of mechanical energy can be applied. The sum of the rotational translational kinetic energies remain constant as long as no external torque on conservative forces act within the system. Next is the calculation of the angular speed and tangential speed. Angular speed, or the W, it is the rate of change of angular displacement, and it is related to the tangential speed, or B, by the formula tangential speed equals angular speed and the rate where is r is the radius. The angular speed can be calculated using the formula. The angular speed equals data over t, where data is the change in angular displacement and the t is the change in time. The tangential speed of the point of rotating object is determined by multiplying the angular speed by the radius. So this is the example. Spinning wheel on the bicycle. Example. Imagine a bicycle in motion, especially focusing on the rotation of its wheels. Up As a cyclist pedals, they apply a torque on the bicycle's wheel. This torque results in the wheel's rotation, creating both translational motion, forward movement of the bicycle, and rotational kinetic energy in the spinning wheel. Next is the rolling downhill. Example. Picture a ball rolling down a hill due to the gravity. Initially, the ball possesses gravitationally potential energy as it rolls downhill. This potential energy is converted into energy, forward motion, and rotational kinetic energy as the ball spin. Next is the record player. Example. Think about the record player spinning a vinyl record. The rotation of the turntable provides angular displacement, translating into the motion of the needle along the grooves of the record. This rotational motion is even converted into the sound's energy. So that's all for my discussion. Hopefully, you learn something and understand what I discuss. Thank you. Bye.